So as we start off and coming up on the board, what is scientific notation? Well, scientific notation is a way of expressing really big numbers or really small numbers. So the goal, the objective of the scientific notation is to have a more concise number, to make it a little bit easier to write. Now, once again, what I said, write down the important stuff. Don't write this word for word. When you're taking notes, just write what you feel like is the essential part. So, making really big numbers or really small numbers more concise. That is the goal of scientific notation. Two main parts. This n here. This n will be a number between 1 and 10. And this 10x is the power of 10. 10 to the what power? So n times 10 to the x power. The big thing though, the n, remember, has got to be a number between 1 and 10. Now, are we going to use 10? No. Okay. So maybe that should be corrected. Maybe we should put between 1 and 9, because we will not use 10, because we only have a singles place. And you're going to see that here a little bit, because if we would use 10, we could take it over one more place. Now, to change into scientific notation, to do so, we place a decimal point so that there is one non-zero digit to the left of the decimal point. That is why we don't use 10, because if we would use 10, it would be 2. Okay, it would be 2 digits to the left. So we have one non-zero digit to the left of the decimal point. Then you count the number of decimal places that you moved the decimal point. This will be the exponent. And finally, you need to decide whether the number was less than 1 to begin with, the original number. If it were less than 1, it's going to be a negative on the exponent. If the number was greater than 1, then it's going to be a positive for the exponent. So, the three parts, we have to make a one non-zero number on the decimal point. Then we have to count how many places we move the decimal point, and then we have to determine whether we're dealing with a positive or a negative exponent. So, if we're just looking at this right here, we have a number, 289,800,000. We're going to put that number into scientific notation so that it's a little bit easier, more concise to write. So, as I'm looking up here, I am going to move my decimal point. Now, There's no decimal point in this number. Where's the decimal point at? Where's the decimal point at right here of this number? Advia, where? Which very end? This very end. So here's where my decimal point is. Now I am going to make a non-zero one-digit number to the left. So I'm going to move my decimal point to right here. Okay? So as I do so, I get 2.898. Now, why did I not write all of those zeros? Because you're going to see later on this week, due to significant figures, those zeros are only placeholders. Okay, they're only placeholders. They are not significant. So, I need to count how many places that I moved the decimal. How I do that is I just jump it. 1, 2, 3, 4, 5, 6, 7, 8 places I move that decimal point. So my exponent is going to be 10 to the 8th. Now my final thing I need to decide, was that greater than 1 or less than 1? Obviously that number is in the 100 millions, so it is greater than 1, so it would be positive 8. So converting that into scientific notation, I get the number 2.898 times 10 to the 8th. Now the second one on the bottom. Second one on the bottom, I move my decimal point to right here. It's got to be a number that is between 1 and less than 10. Well, 5 fits that bill. I look and I say, okay, I jumped 1, 2, 3, 4 spaces. So as I jump 4 spaces, my exponent's going to be 4. Is that number greater than or less than 1? Obviously, it's less than 1, correct? So that is going to give me a negative exponent. So my answer would be 5.67 times 10 to the negative 4th. Now working the other way. Working the other way. Changing from scientific notation to a standard form, we simply move the decimal point to the right for a positive exponent and move the decimal point to the left for a negative exponent and use zeros to fill in. So positive exponent, move it to the right. Negative exponent, move it to the left. Fill in the places that you've moved it with zeros. So given the example up top, 5.093 times 10 to the 6. 5.093 times 10 to the 6. What I would be doing here is I'd say, okay, I'm going to write my number, 5.093. I'm going to move it which direction? To the right, because it's a positive. So as I jump it, I jump 1, 2, 3, 4, 5, 6. Then I'm going to clean it up. So my new number is going to be 5093000. And I just put my commas in there to separate my number a little bit. Now for the second one, 1.976 times 10 to the negative 4. It is a negative value on my exponent, so I'm going to be jumping my decimal to the left. So there's 1, there's 2, there's 3, there's 4. Fill in the zeros. So I'm going to get 0.001976 as my new value. Now, like I said before, hopefully you've seen that before. I'm sure somewhere in math you've done scientific notation, but I just wanted to review it just a little bit, okay? You're going to see we're going to go over metric conversions later on too. I know you've dealt with metric conversions, but we're just going to review it. We're going to add a little bit more too. We're going to do a little bit above and beyond what you're used to doing. Okay? Now, I'm going to give you a second here. Just have a quick learning check. What I want you to do is just number in your notes and write the scientific notation for these 5. All right. Now, I can't remember. I didn't put it, so I couldn't remember if I had on this slide the answers or not. So what we're going to do is just go through and check those. For the first one, 4.05789, and I moved it the decimal 1, 2, 3, 4, 5 times 10 to the 5th. The second one, 3.872 times 10 to the 1, 2, 3, negative 3. Now the third one, I only have 3, so I actually don't really need to put a decimal point, but I move that 1, 2, 3, 4, 5, 6, 7, 8, 9 times 10 to the 9th. Now the fourth one is possibly the toughest one on here, because how far did I move my decimal point? I didn't. I did not move my decimal point at all. So that is 10 to the 0. And finally, the last one, 4.78260 times 10 to the negative 1. Now here's a way, folks, too, that you'll see that I do learning checks here. I say, are we all right? We got thumbs up? So, if you're good to go with these, right now, give me a thumbs up. If we're okay with scientific notation. Okay. What got you confused? You don't know? All right. Do you understand now what you did? Okay. We'll get more examples of these. You'll have a homework assignment on this, folks. You'll have a homework assignment that you'll have a little bit of time next period to work on it. So there'll be plenty of time to ask questions if you're struggling a little bit with this. Now, let's talk about measurements. Let's talk about measurements. Important things. Every measurement, there is a number followed by a unit. We do not have what I call naked numbers most of the time. We need units to go with our numbers. And those units are derived from whatever piece of equipment you are measuring with. If you remember our skills review worksheet, we were measuring with a graduated cylinder, so those units would be milliliters. If I'm using a ruler to measure, there could be a couple of things. I could be measuring in inches. If I'm using the metric system, the SI, I would be measuring in centimeters probably. So depending on what the instrument is you're measuring is depending on where you get the unit. We have SI bases. And here are just 5 of the SI bases that we will deal with in here. Length, mass, volume, time, temperature. So when we're talking about lengths in the metric system, we're going to be discussing meters. When we're talking about mass, we're going to be talking about grams. Volume will be in liters. Time is in seconds. Temperature in the metric system is based on degrees Celsius. Now we're also going to have a measurement that's called Kelvin that we'll learn a little bit later when we talk about temperatures. We're going to have Kelvin, and Kelvin is very similar to the Celsius scale, other than the fact when we're dealing with Kelvin, we do not have any negative values. Every value is positive. That comes in handy when we're doing some mathematical calculations later on. Okay, so we'll discuss the Kelvin scale also. Here we go. Just talking about what we just said there. Now, mass versus weight. Are they the same? Are they the same? No, they are not the same. Okay? Mass is the amount of matter. We get the mass of something using a balance. Weight is the force that is exerted by the mass, only present with gravity. Now, weight is measured in pounds, and we measure that with a scale. Now, at one time or another, maybe you've heard something about weightlessness. They use that term a lot with astronauts, like this individual here, okay, because he's weightless. The reason? There is no gravity. Okay, there is no gravity. So, the force on the mass would be none, because gravity is not existent when he was up in space there. Well, I don't want, there we go. Tools for measurements. Okay, just some checks here. Which tool would you use to measure the temperature? How about the thermometer? What about the volume? I see a graduated cylinder there. Could I measure the volume using this? A measuring cup? Yeah, I could, but this is an important point. Okay? Important point. If you are in the laboratory setting and you're measuring, which do you think is going to be more accurate? Measuring using a beaker or a graduated cylinder? Graduated cylinder, okay? I find people as we go through measuring stuff out in their beaker, and I say, whoa, 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 give me a time out here. I want you to measure that in your beaker, and they'll measure it, and I say, okay, now convert that or pour that into your graduated cylinder and tell me how close you were to being accurate. Okay, and it's pretty surprising because once you think you're right on in the beaker, you pour it in the graduated cylinder and you could be maybe 5 milliliters off at least. Measuring time. I'm going to guess that stopwatch up there. Measuring weight would be the scale. Learning check. Go ahead real quick in your notes. Match the correct ones. L, M, or V. L, M, or V. What you gonna put? Where are you gonna put it? A bag of tomatoes is 4.6 kilograms. That is a measurement of mass. A person is 2.0 meters tall. Length. A medication contains 0.50 grams of aspirin. It's also a mass. A bottle contains 1.5 liters of water. Volume. Very good, folks. Now, what are some of the U.S. units that are used to measure the following? Because we talked about the United States, even though we accepted the metric system, when was it? Anybody remember when we accepted the metric system? That should be in your notes somewhere. 66, right? 1866, if I remember right. Okay? Even though we accepted the metric system or adopted the metric system in 1866, we still don't use it. Okay? Length. We use inches. We use feet. We use miles. Volume. Okay, what do we use for volume? Okay. How about centimeters cubed? Isn't it length times width times height? Okay. Well, I guess centimeters cubed, that would be metric. Inches cubed. Okay. Weight. We talked about weight. We measure in pounds, right? Temperature. We have Fahrenheit. We use degrees Fahrenheit. So even though we've adopted the metric system, we don't use it. Just some of the metric prefixes that I'm sure you folks are familiar with. Kilo means 1,000. So 1 kilometer is 1,000 meters. Centi is 1/100th. So 1 meter is 100 centimeters. Milli is 1/1000th. So 1 liter is equal to 1,000 milliliters. Now, here is some different metric prefixes. Now, what I'm going to give you time to do is I want you to copy these into your notebook, Okay? Copy these. I'm not so concerned with this column right here, this multiplier. So this column to me is not as important as the first three. What I would like you to do is put those first three in there, and I want you to also add one right here, okay, that is not here, the base. Okay, base goes right here in between deca and deci. So go ahead and add those, write these into your notes so that you have them in your notes. Okay, when you look at these, ladies and gentlemen, now we are pretty familiar with this area. Okay? We're pretty familiar with that area. Kilo, hecto, deca, base, deci, centi, milli. I know you've done metric conversions with that. However, we are going to go above and below that comfort zone that you have there. You know, mega here. Giga, tera, peta, exa. Okay? Probably the most common areas where you'll see this is a gigabyte of memory, a terabyte of memory. All right? Now we can go the other way. Really, really, really small numbers. Micro, nano, pico, and it was asked, pico is also called micro, but I see it as pico more than I ever see it as micro. Femto, alto. Now, the reason I wanted you to copy down these here, this column right here, the reason I wanted to get you this column right here is that's what's going to be used to help you convert metrically. Now, when we were used to metric conversions, you know, King Henry died by drinking chocolate milk. That's how I was taught when I was a little kid, and I remembered it ever since then. And you move the decimal places however many you jump, right? Remember doing that? Now, it's a little bit different because when we get into these bigger ones, okay, when we get into these bigger ones, look right here. One is a 10 to the 6 and one's a 10 to the 3. That means that there are 3 jumps in between those two. All right? 3 jumps in between those two. And you can notice as we get down here to the smaller ones, they're jumping by 3 also. So, if I am going to jump, let's say that I have 30,000 kilometers. Okay? And I want to put that into megameters, which is the very next one. I see that from kilo to mega is how many jumps? 3 jumps. Okay? 3 jumps. Go ahead and take a break. We'll discuss this when you get back from break. All right, so once again, here we go. We said that from kilo to mega is 3 spots. So I am going to go 3 jumps. All right, but I need to know which way I am jumping. If I am moving up on my scale, I am going to move the decimal to the left. If I'm going down on my scale, I move the decimal to the right. So if I am converting 30,000 kilometers into megameters, I'm going to jump it 3 to the left. So 30,000 kilometers is equal to 30 megameters. So it's still the same idea that we're jumping the decimal place. It's just that we're going at different increments. Now, let's say that I have a very small number, 0.000157 centimeters, and I want to know how many micrometers that would be. How many micrometers is that? Well, let me get this stuff off of here. I am starting at centi, which is 10 to the minus 2, and I'm going to micro, which is 10 to the minus 6. So how many jumps is that going to be? 4 jumps. What way am I jumping that? To the right. So 1, 2, 3, 4. 1.57 micrometers. Now, like I said before, I want you to put base in here and make sure that you know that base is 10 to the 0. Make sure you know that base is 10 to the 0. But I think that you should be able to do your metric conversions with this bigger scale here. Now, I also, if you forget where this is at, okay, I also have a copy of this chart somewhere on the website under measurements and calculations. On my website, this chart is somewhere. All right. Dun, dun. Moving on. I just put this slide in there to show you some different metric conversions here dealing with, height, volume, and weight. You don't necessarily have to write this down, okay? Quick learning check here. Go ahead and answer those 4 questions in your notes. On my learning check here, 1,000 meters is equal to, dun, 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 dang it, is equal to letter B, a kilometer. 0.001 grams. So that is letter B. 0.001 grams is equal to A, milligram. 0.1 liters is equal to 1 C, 1 deciliter. And finally, 0.01 meters is equal to B, a centimeter. A centimeter. I'm going to show you here, okay, the reason I put this slide in there is we're going to talk about where we use some of these measurements of length here in chemistry. If you look, here is a water molecule, okay? Here is a water molecule. It's got the little ball molecules. We'll do this later on using those, but little molecule there. The distance between, right here, the oxygen and the hydrogen. We're talking the nuclear, the distance between the nucleus of those two elements, the hydrogen and the oxygen, is 9.4 times 10 to the minus 11th meters. Well, we don't want to use that big of a 10 to the minus 11th, so we have converted that into nanometers. That distance is 0.094 nanometers. Okay, 0.094 nanometers. So very, very small distance. Okay. I'm not going to do, we can do those metro conversions, okay, so we don't need to worry about those, okay? Here we're going to just talk a little bit. What would you use, okay? If you were going to measure your height, what would you use? What do you think? Anybody? Anybody? What do you think? Just got to randomly call on people? All right. Let's see, who do I want to pick on first? All right, what do you think? What would you use, Gavin, if it were you? I would use meters myself. I would use meters. You probably could use millimeters, but that would be an awful lot. Okay, obviously we're not going to use a kilometer. How about your mass? How about your mass? Rachel? Huh? Kilograms? Yeah, probably. Because I'm sure it'll be a lot of grams. I don't really know how many grams I would be, but I would say kilograms would be a good one to use there. The distance between two cities? Kilometers? Okay. Well, yeah, unless they're not real far apart, but still, you know, still kilometers is probably good. You know, even if it were here to Coldwater, we'd still use probably kilometers. The width of an artery. Now, probably we could go even lower, but the smallest one here is millimeters, right? We could probably even go lower than that, but of the choices we're given here, millimeters I think is the best one. All right, that's tomorrow, okay? That's tomorrow. So,